I hope you're all having a great day. I am Mr. Ish. Thank you for joining me for this video. We have recently looked at this probability density function concept where we were looking at the continuous random variable, the capitalized X. Well, that can be very well annotated as a capital T, a random variable, when we're talking about times, wait times, the average wait times. There is a specific concept with regards to the probability density function where you can look at the average values. You know, the average value for a probability density function, or you may not know but now you do, would represent, that average value would represent the centrality of that function. The entire graph, if you were to look at a specific function and you know it's looking something like this, we're looking here from 0 up to whatever specific time t, there might be a specific value over here which would be the central value, the average value, and that would be right here, x is equal to this mu. This mu, or mu as it's pronounced, is a Greek letter alphabet which represents average. It is the annotation for average, and you're seeing that right over here. For a specific function with regards to time, you have a value here in terms of the output which is 0 for time is less than 0, but you have a specific output here which is this 1 over mu, or mu to the power of minus 1 times e to the power of minus t over mu, which is an exponential function for time which is greater than 0 minutes, greater than or equal to 0 minutes. If the average wait time, the long run average value of a random variable, a continuous random variable t, is 9 minutes. Based on this 9 minutes figure we've provided you and this specific function which is provided you, you know over here this part right here will not apply, because if you're looking here at wait times, you could be doing a wait time in a store. How long does it take for you to get served? Or a wait time on a phone call. How long does it take for you to reach customer service? Or a government office, you're phoning over there. How long will it take for someone to respond to you? That's exactly what we're talking about. You know you're not going to be looking at values which are less than 0 in terms of time, but you'll always be looking or assessing wait times, average wait times for those values which are greater than 0. You can have no wait time, in which case t will be equal to 0. You can have an indefinite wait time where you're waiting for hours, or you can have a reasonable wait time where you're waiting for several minutes. We have to apply all of this here with regards to these two specific probabilities. We have to find the probability that a given person calls. Let's talk about phone call. A person calls and they're waiting for a customer service. What's the probability that they'll wait less than 2 minutes? You can look at that in terms of this expression here. What's the probability, as our second question, that they will wait for more than 6 minutes? We have to find these two probabilities, and let's look at that. But before we can even address that, we have to know what our function is. We're looking here at the very top part. Our function very well is this item boxed over here. If you eliminate this minus exponent, you're looking at 1 over mu, e to the minus t over this mu. And you know here, this right here, 9 minutes is very well your mu value here. And everything here is with regards to an exponential model. Your thing becomes 1 over 9 e to the minus t over 9. This right here represents the function which will integrate to help you solve both of these. You could very well look at everything like this. You're looking here, there's f of t dt, but we already have these values, so we can very well easily do this with our function we have over here. I just need to create a little bit space. Question number A. We're looking here, probability t is less than 2, greater than 0. What's the probability that I phone and I'll wait less than 2 minutes? It doesn't have to be a realistic model. It doesn't have to be hypothetical. It could be something, nothing more than just learning experience. We're looking at this integral right here. 1 over 9 is pushed outside. How do you write this in integral form? In limit form, it's 0 to 2. And then you have e to the power of minus t over 9 dt. You can do polynomial substitution. If u is equal to minus t over 9, then du is equal to minus 1 over 9 dt, and dt is equal to, you take this on the other side, minus 9 du. You must develop new limit values, upper and lower. Here's my lower, here's my upper, everything with regards to this. When you put 0 here, u1 is 0. When you put 2 over here, you're getting a minus 2 over 9. Now suddenly you're looking at this. You have a u1 which is a 0, you have a u2 which is a minus 2 over 9. Now we have a larger number here in the lower limit, smaller number in the upper limit. We have e to the u du, and we have a minus 9. We'll bring that minus 9 over here. When you're looking here at this minus 9, 1 over 9 is nothing more than a minus 1, because everything cancelled out. I want to use the properties of integrals and their limits by bringing in a minus. If I bring in a minus and I'm looking at everything here, I can flip my intervals around, so I have a good setup here. E to the u du. That's exactly what we have. The minuses will cancel. So I'm looking here now at minus 2 over 9, 0 e to the u du. And when you integrate this, this is easy. It's just e to the u. Do not resubstitute back your u. Leave it unsubstituted, but keep these new limit values, 0 and minus 2 over 9. When we integrate this, we have e to the 0 minus e to the minus 2 over 9. When you get this numerical value, it will give you the probability of this first part question we're looking at. Let's do this part first here. We'll do 2 divided by 9 minus, we'll do shift and then natural log, we'll get the e on it. We'll save this value. Now we do e to the power of 0, which is 1, minus that. I'm getting a 0.199. 0.199 can be very well rounded to 0.2. How do we verbalize this probability 0.2? You can verbalize this as such. 20% of the time that you will call, you will have to wait less than 2 minutes. 80% of the times you will call, you will wait, or the customer will wait more than 2 minutes, right? If you're calling 100 times, 20 of those times you'll wait in this time frame right here, less than 2 minutes. But 80 of the remainder times you try or calling, you'll always wait more than 2 minutes. So the probability of a customer calling and waiting less than 2 minutes is only 0.2 or 20% of the time. So this question right here is done. Let's look at this one right here, the probability where you or I will wait more than 6 minutes. Remember here, this t is capital. It's not my variable in terms of this dt or this lowercase t. It's my random variable. We're looking here at this. Again, our expression is this 1 over 9. But how do we annotate this now in terms of a limit? We're looking at time greater than 6 minutes, which means we're looking from 6 up to infinity. Do you see that? 6 up to infinity. You could wait an indefinite amount of time from 6 onward. And that's exactly what we're exploring. Minus t over 9 dt. You have to use polynomial substitution again. U is equal to minus t over 9. Du is equal to minus 1 over 9 dt. And dt is equal to minus 9 du. You have to get these new values here, and we will. Everything with regards to minus t over 9. If you're here looking here, this is t1, t2. We're looking for u1, u2. Put everything right here. You'll have a minus 6 over 9. And here you'll have a minus infinity over 9, which is minus infinity. Why don't we just write that as minus infinity? And that minus 6 over 9 can easily be simplified to minus 2 over 3. So let's look at it. We're looking at 1 over 9. We're looking here at u1 and u2, minus 2 over 3 and minus infinity, u1, u2. We have e to the u du, and du was minus 9. Again, this minus 9 and 1 over 9 cancel out, and you end up having here nothing other than a minus 1. But I don't like the setup of these limits. I want to have the smaller number here and the larger number on the top. I'll bring in a minus. I'll hit everything here with a minus 1, and it'll eliminate that minus, and we'll end up getting minus infinity here and minus 2 over 3. You know this rule of definite integrals, minus 1 allows you to flip the interval around. You have e to the u du. Let's do this definite integration. We're looking at e to the u from minus 2 over 3 to minus infinity. Or we should be saying minus infinity to minus 2 over 3. So we'll do that, e to the minus 2 over 3 minus e to the minus infinity. But this right here is wonderful. It'll zero out because you know you're looking at 1 over e to the infinity, which is 1 over infinity, and this right here is equal to 0. So technically our definite integral with regards to the antiderivative is just this. This right here is your answer. But if you get this in terms of a numerical value, it'll bring in some perspective. Just do 2 divided by 3, you have a minus, and then invoke the exponential application. You have 0.5134. 0.5134. What does this mean? This is the probability that you will phone and you'll wait more than 6 minutes. But we can convert this into 51.34%. A person, you, me, or anyone calling, 51.34% of the times we will wait greater than 6 minutes. But if you take this and you minus it from 1, and we're looking here at 48.65. The other end of the story is 48.65%, where you will not wait 6 minutes, you wait less than 6 minutes. Anyhow, if I phone at this number, 51.34% of the times I'll wait more than 6 minutes, but 48.65% of the times I'll wait less than 6 minutes. But the probability is more that you will wait 6 minutes more. Remember, you could be waiting hours, but definitely it's 6 minutes or higher, and that's the probability that we've determined. But you've seen here how the average value concept has come into this probability density function, and that was the core point I wanted to demonstrate in this video, and hopefully you understand it. I hope you enjoyed it. Thank you for watching. Have a good day.